Alright, so most of Chapter 8 is really just a lot of vocabulary, and the book doesn't really do a good job of emphasizing this vocabulary. Also, the book's exercises focus on a lot of silly problems like computing the Wronskian of two functions. As we saw, if you have two functions, the only way they're going to be linearly dependent is if one is a multiple of the other. So why do you have to compute a determinant of some matrix? That just is idiotic, to be honest. So I built these notes so that kind of talk about the qualitative nature of what we're going to be doing at the end for the rest of the course. And that's solving higher order linear equations. But understanding some of these vocabulary terms is important as well, to kind of just to get your brain into the right frame of mind while we're doing these problems. But in the end, you can honestly do everything from the rest of the course with very minimal understanding of these notes. These notes are very supplemental. They're extra. All right. They're just intended to help each of you in your own way. So everybody needs a little bit of help in a different way. So more detailed notes gives it more chance for more people to see something that makes something click. But really, it's focused on the vocabulary. So we're talking about linear differential equations, and we've already seen these first-order linear equations. So you have y prime plus some function times y equals some other function. That's a linear equation, first-order linear equation. We want to talk about this expression on the left side of the equation that involves y and y prime, and later y double prime, y triple prime, and so on. This is an operation. It takes a function y and it creates a new function from y, some of its derivatives, and maybe some other functions. That's called an operator. So we call this expression L of y means take y and create this new function, y prime plus p of xy. That's what's called a first order, because the highest order derivative is 1, linear differential operator. The linearity is actually quite simple. At the bottom of the page, we prove what means to be linear. All that means is it takes linear combinations to linear combinations. That's what we see in part 3. This is what I mean. L takes a linear combination of two functions and gives back the same linear combination of the image of y1 and y2. So it preserves that. For example, one of the major mistakes many students make is algebraic mistakes, like the square root of x plus 5 is equal to the square root of x plus the square root of 5. That's false. Square root function is not a linear operation. You can't distribute it over a sum. Linear operators are things you can distribute over a sum, and you can factor out constant multiples. That's all that it means. So in general, what I'm kind of emphasizing here is, how do you recognize a linear operator? Well, it's some kind of expression involving function y and many of its derivatives, but the point is every term, remember term means separated by a plus or minus, you either see a y or you see one of its derivatives, and that's it. Maybe it might be multiplied by some other function, a coefficient function, like 5x or 3x squared or e to the x. Those functional coefficients are okay. That's what p of x is up here. We have y prime plus p of xy. P of x is a functional coefficient. It's not just a number in this case. It could be some function. But it's a coefficient of y. It's something we multiply by y. So as long as you see y and each of its derivatives appearing in only one term by themselves, and when you see them, you only see them to the first power, that's what a linear operation is. That is what is required so that you can simplify. You plug in a linear combination and the output is just a linear combination of the outputs. That's all it is. So again, a general second order equation looks like this. First term, we have a term with a second derivative, you have a term with the first derivative, you have a term with a function y itself. And then the first derivative and y have some coefficients multiplied by them, and on the right side of the equation there's some other function, phi of x in this case, the notation we're using. You may ask, well, why don't we have a coefficient on the second derivative term. Well, the point is, if we had some function here on the y second derivative, we could just divide the equation by that function and then simplify it, and then we have an equivalent equation, but now the first term doesn't have a coefficient. That's why we never put anything there, because it doesn't matter. We can always change the equation algebraically so that's not there. What we're really going to be focusing on are what are called linear equations with constant coefficients. So in general, let's just come up here. The general kind of equation we're going to see is going to be of this form. Some linear operator acting on y. So what does that look like? Well, it has to look something like this. This would be an nth order linear operation acting on y. Notice, we have the nth derivative by itself, and then we have a bunch of terms with all the other derivatives and with functional coefficients. And they're all raised to the first power. Remember, this notation, the superscript with the parentheses, is just a derivative notation. If I had just had y to the fifth power, that would be the fifth power. But if I have y raised to 5 in parentheses, that means the fifth derivative of y. It's a common shorthand, which we can kind of emphasize here in the notes. Just reminding you. So what happens? Well, if these functions, functional coefficients, if they all happen to be constants, like just numbers, then it's a simpler problem. And we call these problems with constant coefficients. So this is a third order linear differential equation with constant coefficients, because the coefficients on all these functions over here are just constants, 5 and 2 here, and of course the 1 for the third derivative. Another way of making problems easier, or easier versions of the problems, is what if the right-hand side is 0? If the right-hand side is 0, we call these homogeneous functions. I'm going to talk about this more in another video, but this word homogeneous is not the same as we used in earlier chapters when we talked about first-order homogeneous equations. What we're talking about now are linear homogeneous equations. These concepts are two totally different concepts, but we use the same word. And the reason is because the word refers to some kind of scaling factor. All right, you can put in some multiples of things and somehow things simplify. That's all that homogeneous means. So we'll see that again in this case, but it's different than we did in the first order equations. It's a different concept. So the general idea is we're going to be given equations like this. So notice I've changed the functional coefficients to just numbers. These are just numbers now, so this is constant coefficients. So we'll have some equation like this. What we're going to find is that there's a really simple step-by-step procedure for finding a general solution. What we're going to do is we're going to ignore this phi of x and put a 0 there. So we're going to consider the easier homogeneous equation. This is what chapters 9 and 10 tell you about, and it's very easy. These are very easy to solve. All you have to know how to do is basically find roots of polynomial equations, numerical equations. So these are actually very easy to solve. And the idea is the nth order equation is going to have n different solutions, y1 through yn. So we just create an abstract linear combination of those solutions of this homogeneous equation, and we call that y sub h. H for homogeneous. This is the solution of this homogeneous equation. So if I take y sub h and I plug it into L, it'll give me 0. That's the idea. What it does is it introduces n different constants, unknown constants, so that later we can solve initial value problems which require us to have n conditions, like y of 0 is 5, y prime of 0 is 10, n different conditions like that will help us determine those coefficients. So then what it comes down to is, if we have this solution to this part, then all we have to do is add to this y sub h one particular solution of our general equation up here. Just one. We can find just one particular solution. And that's what Chapter 11 talks about, finding a specific kind of function, yp, p for particular, which does solve our equation. The problem is, if you just find this one particular solution, it's a specific function and it may not satisfy initial conditions. So we have to add to it the homogeneous part, and then combined those two terms added together, which looks generally like this, will be a general solution. It solves the equation due to linearity, because the first part L takes to 0 and the second part L takes to phi of x, which we want. But it has these constants in it, which now can be used to figure out what they should be in order to satisfy initial conditions.